வீடியோ தெரியலமா பாருமா.
Yes, sir.
Okay, no issue. Good afternoon to all, dear participants, respected chief guest of today event, Dr.C.Retna Raj, Professor, Department of Chemistry, Indian Institute of Technology, Kharagpur, and respected Dean Madam S. Kutirani, respected Head of the Department, Dr. T. Iswaramurthy, and dear participants, good afternoon to all. It is my pleasure to welcome today our chief guest, Dr. C. Retna Raj, and on behalf of Department of Chemistry, B.S. Abdur Rahman, Crescent Institute of Science and Technology, on behalf of our participants, I welcome you all, and I welcome our chief guest. Thanks a lot for your kind acceptance during this pandemic period with your busy schedule, sir. Now I hand over the session to Aisha.
Sir, shall I start?
Yes, please.
Good evening, everyone. It's my pleasure to be a moderator for this session. On behalf of the Department of Chemistry, B.S. Abdur Rahman, Crescent Institute of Science and Technology, I would like to extend a very warm welcome to all of you for the 10th day of the 14 days FDP program on Material Science and Nanotechnology, MSNT 2020. Let's start the session with a famous quote of Sir Albert Einstein. He has stated that education is not the learning of facts, but the training of the mind to think. The important thing in life is to never stop questioning. Having this in mind, let's utilize this FTP platform today. Our speaker for today's session is Professor Dr. C. Retna Raj, Department of Chemistry, Indian Institute of Technology, Kharagpur. Before the start, let me give a brief introduction about our speaker. Professor Dr. C. Retna Raj completed his bachelor's in chemistry from Madurai Kamaraj University. He pursued his master's degree from Anonmaniam Sundaranar University. He earned his doctoral degree from Madurai Kamaraj University under the guidance of Professor R. Ramaraj. He has published around 108 papers in highly reputed international journals. He has patented his works and has around 7 patents, namely 1 US patent, 2 Japanese patents, and 4 Indian patents. He has an H-index of 34. He has published his research interests and works as 2 chapters in 2 books. He is the editorial advisory board member of ACE's Applied Materials and Interface since 2020. He is also the associate editor of the Journal of Chemical Sciences, INAS, since 2019. He has been awarded the Chemical Research Society of India Bronze Medal in the year 2013. He also received the Indian Society of Electroanalytical Chemistry Award in the year 2010. His research interests include electrochemistry and functional materials, design and development of new functional materials, amperometric biosensors, electrochemical energy conversion and storage, supercapacitors, and metal air and metal ion batteries, electrochemical water splitting, etc. With this short bio sketch, now I call upon the Professor Dr. C. Retna Raj sir to take over the session. Thank you, sir.
Thank you very much for your introduction. It's a great pleasure for me to meet all of you. Maybe you'll not be able to meet face to face, remotely connected, and share some of my interests in the research work that I have been doing.
Sir, please share your slides, sir. Please.
Yeah, just hold on.
Okay, no issues. Yes, sir. Please, full screen. Yes, yeah. Now it is visible. Yes, sir.
I will not much talk about my research. In the initial, I will give a little bit of advertisement for my lab and electrochemistry, and then I will be a typical history teacher for quite some time. And the later part, I will share what we have been doing in the last couple of years and so. So I hope you will enjoy. In case if you feel that it's boring, you put in the chat box. I will turn my talk in a different way. I will try to turn my talk different way. The reason why I say is that the electrochemistry is not well known to many of the college teachers and students. So for some of you, it may be a kind of a boring, but I will try to engage you and motivate you to enter into the field of electrochemistry and enjoy the beauty of electrochemistry. Okay, so thank you very much, Professor Iswaramurthy and Professor Vasimalai, and thank you for Aisha for sharing, for introducing me. I put the title very generally, the functional materials for electrochemical energy storage device. It's a very wide topic. I will not be able to cover the entire thing. So I will be restricting myself to a Zinc Air Battery. I'm not sure how many of you have heard about this, and supercapacitor. I hope you should have heard about the supercapacitor at least in one point of time. If you have studied physics in your ancillary lab, you should have come across the supercapacitor. Okay, right. So before I go to that, it's my duty to bear from my end. Some of you might not be knowing that where is IIT-Kharagpur, right? I'm basically from West Bengal, right? It's close to Bangladesh. And in one tiny part, there is a, what we call, it's over here. The district called Paschim Midnapur, and then go to this place, then IIT-Kharagpur, and here I have shown here. So this is for the brief for those who are not familiar with where is IIT-Kharagpur. Okay, that's the first of the IITs. So I will be able to show here. This is a historical place. You can see from here, bondage to freedom, the nation's journey. The first IIT that was established in a place where our freedom fighters were put into prison. Okay, I will not go into the detail. So you may, when you are coming to Calcutta or another place coming on the side, you can drop by Kharagpur and can have a visit to our campus. It's a historic place. So before going to my topic, let me acknowledge these are the soldiers who work for me in the lab. I'm not going to tell all their names. That will take part of my time. The funding is from SCRP, CSAR, and IIT-Kharagpur. So this is my outline. So I'll briefly mention about my research group and what I call is the library that we have developed, what I call the functional material library. And I will give one slide of the beauty of the electrochemistry, as a glimpse of the beauty. And then I will go to the electrochemical energy storage device, particularly. I will restrict to zinc based device. I will give an overview. And then I will give a little brief basic on the fundamentals of the Zinc Air Battery and a little later on the supercapacitor. And then I will take you to the functional materials, what we have synthesized, that's outcome from our lab. This slide describes that what we have been doing. So we call this the functional materials and electrochemistry lab. So we synthesize functional materials and look at the electrochemical application at a different angle. So that include fuel cells, electrocatalysis, batteries, supercapacitor, water splitting, not limited to this one. We also work on the biosensor. So these some of the publications, some of them are listed here. That's it's a representative publication from our group. So what I call this is a functional material library. Over the year, what we have synthesized and what we have studied, and we put in this, I call it a library. Starting from maybe 2005 onwards. So what the outcome of the work that we do, that we compile together, I call this as a materials library from my lab. That is a functional materials and electrochemistry lab. That you see the pictures. I'm not going to give you details and then how we synthesize, what and all we do. That the time is very limited. I'm not going to that one. Okay, so let me give you a brief introduction, right? So what I call is the beauty of electrochemistry. So I'm not sure how many of you have come across this window. So what we call the electrochromic window. This is typically for the aircraft window. So usually what we have, a shutter, manually you pull down and push it up if you want to see outside or if you do not want to see. Those who have traveled by aeroplane, you will be able to see that. Now, to appreciate electrochemistry, here what we have a window that is specially made, what we call say electrochromic window. You don't need to pull down and push up the window, just press the button, whether you can make it transparent or semi-transparent or opaque, just one button. So that is basically the underlying principle is the electrochromism, or what we can say electrochemistry. So the other one what we have, I think I don't need an explanation for this. You should be knowing the Oscar award, and the other side what I put there, the mobile phone. Those who have the mobile phone with a metal body, and many of you may have a fascination towards a gold-plated the mobile phone. So the basic the underlying principle that comes there is a electroplating. That's again, that is a, I would say that is a beauty of one of the beauties of the electrochemistry. And another one, that is what we have, the corrosion. You may ask, is it beauty? Yeah, in my view, this is another beauty of electrochemistry, right? What we have, a metal that is hanging or outside, a water droplet comes in there, that's an electrolyte, and then the electrode reaction takes place spontaneously without applying any potential, without you giving a electrolyte. That happens, finally a product is formed, whether it is advantageous or disadvantageous. In my eye, that is a beauty of electrochemistry. And then the fourth one, so everybody will appreciate that, so electroorganic synthesis. Yeah, you can control the potential or the current in your electrochemical cell and tune according to your requirement and synthesize as much as you want. This is one of the very upcoming field. If you look at the literature, you'll be able to see that the electroorganic synthesis is the one of them, the upcoming field. So then the fourth quadrant, what I have shown is that basically a beauty of an electrochemistry. Right, let me come here. So this I put all the what I call them is there's a pillars of electrochemistry. So you start from Galvani and end with Nernst. So you cannot deny their contribution in the field of electrochemistry and overall in the field of chemistry. Right, I'm not going to explain all of them. That itself, one itself is a lot of history is there. Now go here. Let me get into the topic. Right, the title was what I say that is energy storage devices. Now you may have a question: why do we need an energy storage device? Why do we talk about that one? I think most of you are well familiar with this kind of words, the buzzwords, right? The energy demand and growth projection. This is not the graph that made by me. This is already established and put in the standard journals, and it's available there. If you look at the first, just a minute, please. Okay, the first the plot that I have shown is the energy demand in metric tons oil equivalent, and here you have your the years. So the energy demand, a projected energy demand, that is, you can see that in 2030 how much is the requirement. On the other hand, if you look at the other side, other quadrant, you see that the production and consumption. So you can see that the consumption is huge with respect to your production. So what I want to say is that we have a lot of demands, but the production is limited. This is a very limited way I'm telling that we can talk about much on this topic. So I'm not going to the much details of that one. What I want to say is that our society's energy demand is huge, but the production is very less. Mostly we depend on the fossil fuel. So if you look at the pie chart, what I have shown here, this is based on the 2017 for the survey. That what it says is that you can see the total contribution of the supply, primary supply by share. That is, most of them comes from the fossil fuel. So the main question is that how long you depend on the fossil fuel. Not only that, does this fossil fuel is safer to use? That's another big question that we need to use it. So you may ask the question, what is the problem all this at once? Right? If you look at the environmental issues, And other issues that is associated with the use of the fossil fuel is this basically what we call the global warming, the greenhouse effect that is basically coming from the burning of your fossil fuels. Now look at this one. We continuously burn because we want to live in a comfort zone. Well, I mean, 10, 20 years back, we used the public transport. Today, we don't want to use the public transport. We want to have our own comfort zone of vehicle. As a result, what we do is that we are basically polluting. So you can read this screen, so you'll be able to understand that what I mean here. The one side is automobile, the other side is the industry. It's not only limited to industry, and many other things comes into there. So how long this will go? Yes, I have a fossil fuel reserve. I can burn it as long as I have. It's not only that, when you're burning, what you're doing is that you are harming your environment. That nobody understands that. So what we should do? Yeah, we need to take a little step. So my talk is a little related to that one. It's a very small fraction of the contribution to avoid the heavy use of fossil fuel cell and use of the renewable energies and its storage. That's what I'm going to talk about it. Now look at here. So what I have here is that I have there are two sides. One is a renewable energy and another is a non-renewable energy. So what I talked about the fossil fuel, all this I'm talking about, there is a non-renewable energy sources. So you talk about the oil, you talk about the coal, you talk about the natural gas, and so on. These are non-renewable. On the other hand, we have a renewable energy, right? What we have a biomass, solar, wind, and many things are there. Now, the major concern is that everybody look at the solar cell. Yeah, we can generate energy. It is true that we can generate energy. Can we use it continuously for the 24-hour requirement, intermittently? So what we need is that we need some storage technologies because your renewable energy are limited to season and time. I say, for example, your solar, your sunlight will come daytime, so you need to harvest and store it. So I'm going to that, the storage technology, not on the energy conversion technology, right? You can read this one. This is a famous quote by Ellen Bowden, who is the author of Chemistry is Electric. Imagine a world without batteries. A teenager walks outside wearing a headphone, tethered to home by a lengthy extension cord. An old man winds his pacemaker like a pocket watch. In thousands of ways, large and small batteries have changed our daily lives over the year. It is yet to come. The revolution is yet to come. We are looking forward to that one. Keeping this in mind, the importance of the energy storage, particularly the electrochemical energy storage devices. So I have shown a diagram. You forget about the name, the name that I have written. There is a plot between a power density and energy density. The next slide, I will be able to explain you what is actually a power density and energy density. So here I have listed some of the energy storage devices. Say, for example, capacitor, supercapacitor, battery, fuel cell. So your batteries and fuel cell have a high energy density, but they don't have a high power density. But on the other hand, the symmetric supercapacitor or asymmetric supercapacitor, generally supercapacitor, it is bridging the capacitor and the battery. Okay. Now I put the diagram in other way around, energy density versus power density in terms of a different way. If you want to charge your battery, it takes a lot of time. But on the other hand, if you want to charge your supercapacitor, it is a few seconds. If you want to charge the fuel cell or chemical battery, whatever the battery that you have, yeah, you need to have a 1 hour to 10 hours of I'm talking about the conventional batteries. But on the other hand, your supercapacitor needs a few seconds to charge them. Now look at here. Look at here what I have. I have given you the battery. Battery is basically, it has a high energy density. I would call this as a battery as a total. It will slowly charge and slowly and steadily supply the energy. You can read that. We don't have much time, so I will quickly have a glance through it. This is all about the battery. Now, another one, what I mentioned, a supercapacitor. This what we have, it's a high power density. So battery has a high energy density. Here what we have is a high power density. Now I would call this as a hare, or what do you call the rabbit. You can quickly charge and discharge it. So there are two kinds of energy storage devices. One is a battery and one is supercapacitor. One has, the battery has high energy density, the supercapacitor high power density. What we need is that we both are needed. I cannot say that turtle is very slow, throw it away. No, the hare is very fast. I cannot run with that. I don't need that. No, it is not that. So what we need is that if both of them are not competing, but complementing each other. We need batteries as well as we need supercapacitor. Now, I hope you will be able to understand the meaning of the power density and energy density. So you can see here, the coffee mug is basically what I call the return of power. You can pour out the content as quick as. That is talks about the power density. On the other hand, my other hand has a water can. The content of the water can is much higher than the content of my coffee mug. But I cannot pour out the content as quick as my coffee mug. I can steadily, slowly pour it out. I hope you could understand what I mean, the power density and the energy density. So I cannot go only with the power density. Also, I cannot go only with the energy density. I need both of them, right? Now look at here. So everybody has your gadgets, your mobile phone, laptops, tablets, video camera, on all others are there. If you look at the timeline from here to here, right? Say for example 83, now 2018, 2019 or 2020, we are going far ahead. So mainly depending on only one thing, that is a rechargeable battery or energy storage device. That's what I mentioned in the beginning, the quotation that I have mentioned that. Now you can see in the plot how it goes there, right? If it is 2050 to 2025, how's the increase in for the demand for the energy storage devices in terms of billion US$. Okay, so now I'm coming to the basics. So what I have so far I have given is a general introduction. Now I will be going with a little bit of a history, right? Those who like history, enjoy. If you don't feel like listening to my history, yeah, hold on there. I will quickly finish it up, right? So let me start with the zinc. This is one of the very amazing metal. That is what we have in the first row D block at the end, right? I'm not going to teach you about the periodic property of zinc. I have picked up zinc because I like the zinc because it has very good properties, right? It's quite cheap because it is the 23rd most abundant element, Earth crust, and 4th most mined metal on the planet. It's quite expensive, inexpensive, not expensive as the other metals. I will come to the next part. You will be able to understand why I'm talking about $2,117 US per ton, right? Reduction potential is, in terms of electrochemistry, it's minus 0.76. The most amazing thing is that I can handle it very carefully, very easily. It is highly stable in aqueous media, so I can handle whichever the way I want, unlike the alkaline metals. The zinc is very stable in aqueous media. Now let us go here. Let me start with a little bit of history, right? I'm not sure how many of you came across Benjamin Franklin, right? Everybody should have come across. When you study your class 8, 9 or 10, or at least in class 11, you should have heard about Benjamin Franklin. In the 18th century, that is 1749. So basically the term battery was coined based on the Leiden charge. I'm not going to, this is typically a capacitor, right? How the charge is being stored in what we call the famous Leiden charge. And then you should be familiar with, those who are studied physical chemistry or inorganic chemistry, a little bit of the fundamental, you should be able to understand this. What I said is that animal electricity by Luigi Galvani, right? I'm not going to the detail of that one. You can see here what he has done is he took two different metal connected to the frog. Okay, he started looking, seeing the twitching of the frog. You can see the animation. What he has taken two different metal connected to each other and hold it, touching the muscles or the nerves of the frog. The muscle of the frog started twitching. Now he put the word that animal electricity. He mentioned that the frog has electricity. From there will be able to generate electricity. This is the first time in history that is electricity from an animal that has been brought to light. Basically, what he has done is he had a copper wire and an iron wire connected together, and he observed the twitching of the frog's leg. Okay, now he comes there. Volta, everybody should be knowing voltas. So he read the discovery, whatever Galvani proposed forward, and he refuted that no, it cannot be the animal electricity. This is something to do with the metal, because you have two different metals, you are connecting to each other, and your frog has some kind of a electrolyte. That's a bit, the water or some electrolyte is there. As a result, there is some reaction between the metal which is being reflected in twitching of the frog. So he completely refuted. So anyway, I'm not going to debate on whether it's animal electricity or bioelectricity. I'm not going to that one. Now, Voltas, what he has done is he piled up copper and zinc and was separated by the pasteboard soaked in salt solution. For the first time, what he has done is the battery was born. Though the battery was coined earlier, so for the first time in 1800, the birth of voltaic pile, that is the battery. So he proved for that. What we call the voltas ground cups, alternative voltaic pile, copper and zinc with the electrolyte alternatively put it there. He demonstrated to Napoleon and his code. And subsequently, there are many other scientists use this, his voltaic pile for splitting water. So his contribution cannot be overthrown. Now let's subsequently what comes there. Our Daniel, everybody knows the Daniel cell, right? I will not go into these are all historical images, the original images. That is during his time, how this was made by changing the anode and cathode, how they could drive electricity from these small funny structures. So basically, a copper sulfate and zinc sulfate separated by a membrane, right? So one problem is that hydrogen bubble formation and the internal resistance. At the end, during this 1849 to 1890, there are 37 different variants of Daniel cell was proposed. Okay, we are not going to see all the 37 variants. We'll come here. Now, this is a William Robert group. He's known for a fuel cell technology. He's the father of fuel cell. I'm not going to the details. What he has done is, from the voltaic cell, what he has done is he removed the copper and put the platinum and replace other electrolyte with the sulfuric acid and nitric acid. The problem here is that the platinum is very expensive, and then when it is connected, in the galvanic reaction takes place, the 1.9 volt, what happens is you will produce your NO2 fume. That is obnoxious. That is not acceptable at all. Now, his contemporary other one came, right, William Bunsen. So what he has done is he replaced the expensive platinum with the carbon, but he eliminated failed to eliminate the gas formation, because you have your nitric acid. As long as your nitric acid is there, the generation of your NO2 is bound to happen. Now, subsequently, what happened? What we have is the dichromate cell, Robert and John, right? I'm not going to the complete history. In the previous one, in all that one, there are two compartments. Now, here what they have done is that replace the two compartments with made it a single compartment, make it convenient, right? You can read all that one. So what he has done is that instead of sulfuric acid and nitric acid, he has taken a chromic acid. That's nothing but the dichromates. What do you call the dichromate cell? Dichromate plus sulfuric acid, you get a chromic acid, and it goes there. You have a replacing platinum with the carbon, so you can get rid of your nitric NO2 gas. But one problem is that because this reaction between your dichromate and sulfuric acid, you will consume all the electrolyte, your power output automatically drops out. So that's a serious problem. Now, this is a historic picture. Thomas Edison used this dichromate cell to operate his phonograph, right? So that is one of the things that, I mean, he is connecting his phonograph with the what we call the modified version of the Donat's cell. Now here comes the electrolytic cell. That what he has done is, we don't need any acid, whether chromic acid or sulfuric acid, nothing is needed. I will make it very simple. That I have a zinc and carbon, MnO2 and ammonium chloride. Made it, that is, he patented it, is in 1866. The fundamental reaction goes here. I'm not going to explain this one. A little lighter side, even during that sign, there were people to pirate the device that Electrochemistry has made. Right? You can see a Western Electric Corporation made a pirated version and started selling in the market. You can imagine that in the 19th century, 1866, there also the bad practice was there. Right. Now coming to almost on the end of the zinc. Now what do we have with the gas nerd? Right. He should be credited the birth of a dry cell. So what he has done is that he made a zinc can as a container, as a negative electrode, and zinc chloride added to avoid the zinc corrosion, and made the dry cell for the first time. And he patented in 1887, commercialized in 1890, and for the first time he got 100,000 order for a dry cell. That's a major achievement at that time, as a birth of a zinc-based dry cell. Right. On the other hand, what we have here is Lewis, 1955. Let me briefly explain the history. That he was working in Canada. Okay, he was in the Union Carbide. He was asked to move to US to work under the Eveready Battery Company to find out, to replace the dry cell. So he was working on, and finally one day he found that, based on the combination what I have shown here, he found that, and he made the energizer, the alkaline battery, and he ran to the nearby toy shop. He bought the toy, the car. So and one car he put the Gassner battery, that's the dry cell, and another car he put the one he made it for the first time. So surprisingly, to the whole campus of the company in the cafeteria, he demonstrated how his battery survives for a long time. So by running the toy battery. So there's the major breakthrough. What we have today is the alkaline battery. That is a father of that alkaline battery is basically the Louis Frederick Urey, right? He patented in 1960, and you will have that, even every one of you will have the alkaline battery in your home or in your lab and in your office. Okay, having said that, let me make a stop there in zinc. Let me come to lithium, right? So zinc is stand there. I will continue a little later after once I finish that, the lithium part. Lithium is a very good metal, but one thing is very notorious is that this is highly reactive. So as I have shown in the diagram, the supply is very less. That's what the lithium scarce. Only 20 ppm in the at first. Now you can recall the cost of your price of your zinc and your lithium. So having said that, let me go here. Quickly go to that. So electrochemistry of lithium was studied in the year of 1912. I'm not going to detail. And you will have the potential of lithium plus is minus 3.05, implying that how it is reactive. Okay. So if you want to deal with, if you want to work with lithium, you need an inert atmosphere or a non-aqueous electrolyte. You cannot do it in open as you did with we do with the zinc. This is highly reactive. So you need a glow box and you need your non-aqueous solvents. Aqueous solution is nowhere for the lithium. Okay, in 1970, Stanley taken some effort. Now you can look at this one. The diagram you can look at. What he has made it, he made an anode lithium and cathode is titanium disulfide, right? So to make a rechargeable battery. So what I'm talking about, a rechargeable battery. It's not a primary battery. It's a secondary battery, rechargeable battery. So to make it very briefly, looking at the material, right? The green color crystal structure that I have shown is a layer structure, titanium sulfide. So he used the titanium sulfide as a cathode, lithium as an anode. So as I said, if you want to work with the lithium, you need an inert atmosphere. He has put everything inside the inert atmosphere, made the battery with the help of a company called Exxon. You might be knowing that one. In 1977, the first battery, that is lithium-ion battery, that is developed by the company, what it called the Exxon. That's underlying one is Stanley, who is there. So basically, the lithium get oxidized, comes and intercalate between the two layers of the titanium sulfide, and it has to go fat. It's a very beautiful chemistry, right? But the device is not commercialized. It's a very early good time. Now he comes there, good enough, right? Everybody should be knowing, right? Who is good enough, right? He came there, right? Instead of having a titanium sulfide, why can't we have something little cheaper, little better material? A major breakthrough came during 1979 to 1980 when the good enough was working in Oxford University. He made it. He kept the anode as lithium. He did not change the anode. He changed the cathode. He could get a very phenomenal improvement in the performance. Now, what's the difference in the material? Both are having a layered structure. Lithium titanium sulfide and lithium cobalt oxide. Both of them having the layered structure. So the underlying principle is same. What I mean is that what we have is that your intercalation, de-intercalation of your lithium. So the sad part of this one, right, little bit of, right, it may be amusing for you. The Oxford did not patent this technology, refused to patent. So what good enough say that, yeah, a few yards away, the Atomic Energy Research Establishment, he walked there and asked that, you see, I have this one, would you like to patent it? Yes, they patented it. But he did not ask for royalty. He just, everything given everything, all the rights to the Atomic Energy Research Establishment without any royalty, right? You may surprise that good enough has published a paper in Material Research Bulletin in the year of 79, right? You may think that what is the impact factor of this journal? No, it may be a 2 to 3 impact factor, right? But it is, he has published the first one in that journal. That's a groundbreaking story. Now let's go here. This is the material. The wonder, I would call it the wonder material, lithium cobalt oxide. You have your lithium and then cobalt oxide arrays. In between the lithium and cobalt can go and come out by intercalation and intercalation. Okay. Now it looks very, fancy, right? Whether Stanley or your this good enough, you have made it. So energy storage problem is solved. No, not really, because you have somebody is in your hand that is lithium. You cannot tame this fellow. This fellow is a highly reactive fellow. So we need to find out a way, right? Now you see here, what is the problem is there. Now you make the device. Yeah, what we have here is a Stanley's titanium sulfide based battery blasted off. Why? Yeah, when your lithium get oxidized, go and get intercalated, passing through your separator, and coming back and get it redeposited in the lithium anode, you are basically, what is happening is a deposition of lithium that grow as a dendrites. These dendrites go and pierce the separator. As a result, a short circuit. As a result, what we have? Your battery get blasted. So dendrite penetrate the separator, reach opposite electrode, short circuit, potential fire hazard. So that's a serious problem. Now what we have, can we replace the lithium with somebody else, right? Can we have a anode which can be tamed? You will have a control, right? Here I have put this anode, what we have, the graphite or the carbon-based anode. Now here comes the Akira Yoshino, the Japanese scientist, right? You can see the picture that where he's working on the battery. In the 1985, the birth of the lithium-ion battery, that's a rechargeable lithium-ion battery for commercial application. Okay, what he did is, he took the petroleum coke, that is your carbon, and then you have your lithium cobalt oxide, that is borrowed from good enough. Make the device, you make it, for the first time, he tested that Yeah, there are two devices. One is based on the Stanley device. Another one is based on Akira's device. The safety test did not fail. It could withstand the much pressure. It did not blast away. Right, that's a major breakthrough in the history of rechargeable energy storage battery. Okay, what we have? This is a cell reaction. What is the operating principle? Again, I'm not going to the detail. I'm not sure how many of you may be comfortable with the reaction, redox reaction that's going on. Now, coming here, these are the three different types of material that is available, that is so far that has been used. Lithium titanium sulfide, lithium cobalt oxide, lithium iron phosphate, right? Now, we'll go here, right? This is the groundbreaking story, 2019 Nobel Prize. That is, three of them got that. They created a rechargeable world. That is, today you and me have the battery, the mobile battery with a Lithiumion battery. That is because of these three guys, right? So Stanley with the titanium disulfide, good enough with the cobalt oxide, a major breakthrough with the company's development, a commercial lithium-ion battery in the year of 1985, a rechargeable battery, right? Now you say that, yeah, that's the end of the problem, everything is solved. That is not so, right? You can store the energy with a lithium-ion battery. That's not so. Now, does the lithium-ion battery arrival in the market solve all energy storage problem? Not really. Now what we have, everybody knows that. I'm not going into detail. So those who have traveled by air in the year of 2016, you might have heard the announcement in the airports, right? Those who have the Samsung Galaxy Note 7 battery, you're not supposed to have it in your baggage, any of your baggage. They're blessed. So the reason is a short circuit by some means, defective fabrication, or the short circuiting because of the interconnection between your positive and negative pole by piercing the separator. Right here, I have given the three reasons. One is short circuiting. Second is overcharging, and the number third is electrolyte breakdown. Right. I'm not going to details because we have a limited time. Right. Does your mobile phone battery last for long? That's a big question, right? $1 million question. Right. Look at this guy. Oh my God, it doesn't even last for a day. Oh no, I forgot to charge the battery. Hey, talk fast, my battery is dying. These are all common sayings, right? As you use your mobile phone, you're bound to say at least one point of time, right? My battery doesn't last long. What I bought it 2 months back, only 2 months back, the battery doesn't withstand not even for a daytime. So we are frustrated. Do we have any alternate energy storage system? Yeah, we need to look at this one. You look at the electric vehicle. So what I talked about the battery for the mobile are the gadget that we have, and the other side is the electric vehicle. So what we have here, lithium-ion battery, 160 kilometer at one start you can go, not beyond that. So what we need to have, we need new generation batteries to get rid of all these problems, to take you, miles with one charge. So there are some in the plot I have shown, zinc air, lithium sulfur, lithium air. So I will bring this one to the metal air batteries. Okay. So for what I have given you two type of batteries. One is a zinc, that's a older version, that's a energy storage device in the past, and then lithium-ion battery, the LNB storage device in the present, what we have been using. So what I'm going to display in the screen is in the future, right? What will be metal air battery? What will be the future of our energy storage? Now, look at the screen, right? It's a very simple reaction. So I have given two sets of diagrams, one on the left-hand side, another on the right-hand side. One is non-aqueous base, another one is aqueous base, right? The non-aqueous base all are alkali metal base, your lithium, sodium, potassium. And this other side, I have aluminum, magnesium, and zinc. So when we talk about this non-aqueous, again the problem persists. because I'm going to use the highly reactive metal. What I need is that the primary is that here I need one anode and the cathode is an air cathode. That's why I call it an air battery. So the function is based on the oxygen that is derived from the atmosphere. So I don't need to give anything additionally. This is a big advantage. But the problem is non-aqueous, this device has a problem. The dendrite formation, blasting, short circuiting, everything is there. On the other hand, here we have aluminium, magnesium. These two are irreversible. For primary battery is okay. But on the other hand, zinc is a good metal which can be used for the zinc air battery, rechargeable zinc air battery, right? The basic function is oxygen evolution reaction and oxygen reduction reaction. I will come to this a little later. Okay. Now, where does this metal air battery stand? I'm not sure how many of you heard about this metal air battery, right? Those who have read newspaper and journals and magazine, you should have come across the hearing aid. The hearing aid available in India, manufactured either in China or another country. The charge is, the battery is the zinc air battery, right? So that's a primary zinc air battery. So now, where does this metal air battery stand in terms of your energy density or your power density? You can look at here. Your lead acid battery is somewhere here. Nickel cadmium, nickel metal hydride, lithium ion, what we have been using. But zinc air has a much better performance with respect to lithium ion, but it's yet to be developed. That's a theoretical and practical is yet to come there. On the other hand, lithium air has a much prospect, but it's somewhat difficult to handle. Okay, now look at here. Let me briefly explain you what actually zinc air battery, how it works. Here we have your zinc anode. Here you have a air cathode. Right, zinc supposed to get oxidized. In the air cathode, what's supposed to take place is your oxygen from the air should get reduced to water. So you should have an air cathode which should be capable of catalyzing the reduction of oxygen that is coming from the atmosphere. And if I want to have a rechargeable battery, I should be able to convert the electrochemically generated water, that is oxygen is reduced to water, and then water should be converted into oxygen so that I don't really need to depend on the atmospheric oxygen. I can cycle this oxygen back and forth. I will be able to generate the power. I hope you would understand. So what is the basic principle of the zinc air battery? The anode, what is happening? In the cathode, what is happening, right? I will restrict to this one. It is more special, the specialized topic. You may not be able to understand much. If you have a doubt at the end, you can ask me, right? I hope I am keeping my time. All right, now you go here, right? What I have, this plot, you can look at this one. This part, what I have shown here, this part is basically what I have is the zinc anode part, and here I have my oxygen electrochemistry. Here, this part, what we do is zinc is getting oxidized and reduced. And here what I have, oxygen is getting reduced and oxygen is getting evolved. This is what is story here. Now, if you see here, what we need is basically, you need a zinc plate. And for the anode, on the other hand, you need to have an air cathode, which should be made up of a catalyst, what I call the oxygen electrocatalyst, should be able to catalyze oxygen reduction and oxygen evolution. These are the two reactions that we need to look at this one. So here what I have shown, what I have here is your oxygen evolution. Here what I have shown is your oxygen reduction here and oxygen evolution here, right? Now let's go. Yeah, this is the basic model of the, the normal laboratory model, the zinc air cell. Now, what is the requirement for a air cathode? Ideal bifunctional cathode. Right, let me briefly put it there. You may not be able to understand the actual terms. You should have a very low work potential. What I mean here is that oxygen should be reduced at low work potential. At the same time, oxygen evolution should take place at lower work potential. I should not waste my energy, right? Let me finish that one. I'm not going to the detail. If you have any doubt, you can ask me later on. So what we have now, we have a two group of catalysts. Platinum-based catalyst for oxygen reduction and iridium or ruthenium based catalyst for oxide evolution. Both are very expensive. So basically, I want to reduce the price of a lithium-ion battery. Now I end up in coming in with the platinum catalyst and ruthenium catalyst. If I want to make the zinc air battery, as a result, what I will have, the overall the cost of this battery will increase. So I need to find out a less expensive catalyst. That single catalyst should be able to catalyze both reactions. That's the idea. Keep in mind that. So single catalyst should catalyze both reactions. So here platinum can catalyze oxide reduction. The iridium or ruthenium can catalyze oxide evolution. Both cannot catalyze both reactions. That's a drawback here. Right. Here I have put plenty of things. You have a noble metal, metal-free, metal non-metal, and non-noble metal catalyst, how we can construct, synthesize, and make the device, right? Now look at here. What we need to do is that we need to have engineering of the catalyst that we synthesize. What I mean in terms of material, what we say is that the heteroatom doping. What I mean is that the heteroatoms put inside the catalyst. Or surface engineering, increase the surface area and bridge the bond coupling between two different entities and increase the fissile mass transport, right? So I hope I'm not talking much advanced. I will go a little faster. Look at here. Look at this slide. Those who are really want to work on material, look at this slide. I will spend some time here. So if you really want to enhance the activity of your catalyst or your material, there are two ways. Increase the number of active sites or increase the intrinsic activity of the catalyst or the material. So there are two approaches. When you synthesize a material, to increase the activity. How do I increase the number of active sites? You change your catalyst support or change the shape of the catalyst or do an engineering, what we call the nanostructuring. I will come a little later on what I mean the nanostructuring. Like you make a pillars or dots, increase the overall surface area so that you will be able to increase the number of active sites. Okay. On the other hand, I can increase the intrinsic activity by covalent engineering. Right. What I have is alloys, core shell or intercalation. You synthesize a phosphide, sulfide, carbide. You change the surface morphology, change the structure, dope the heteroatom, and do the chemical covalent engineering. As a result, you can increase the intrinsic activity. The advantage, both sides are there. Much advantage, I would say that you are increasing your intrinsic activity as a much more advantage. According to the predicted theory, you will be able to get your activity, right? Okay. Let me go here. This is our journey, right? Give me a minute. I will get back to you. This is where we started our journey. Okay, right. You can read it. I will very briefly say that. I say that for the engineering of the catalyst, what we have done is we did some kind of engineering by what I call the surface engineering by alloying and electrochemical de-alloying. This simple galvanic displacement reaction. You start with the copper 2+ and the cobalt nanoparticle, do a galvanic displacement reaction. So here you have your galvanic displacement reaction. You generate your copper cobalt alloy, and then again do another one galvanic displacement. All are playing with the chemistry, right? You have you play with the knowledge that you have. You generate your trimetallic alloy nanoparticle, and then what you do is that you do a electrochemical de-alloying. All this what I call the engineering of the surface to increase the surface area, to increase the active sites, so that I will be able to get better output. So you can see here all the characterization, all the data is there. What way I call say engineering, we tune with the lattice parameter, all that we do that. So that's why I did the alloying and de-alloying. I'm not going to the details of the data that I have given. The electron microscopic image and the XRD pattern is given here for your ready reference. What we have here is a potential how the galvanic displacement takes place. Okay, so we need to test the catalytic activity. That's the primary aim. I want to keep that is that what I need is that I need a air cathode bifunctional catalyst which should be able to catalyze both oxygen reduction and oxygen evolution. So we tested is a typical electrochemical test. Again, I'm not going to the detail. The electrochemical test, this catalyst, yeah, it looks very fancy catalyst, but it's very good in catalyzing the oxygen reduction reaction, right? Very good. You have a durability, activity is fantastic. You have a 5-hour durability. You check it, you have a very good durability, activity is fantastic. But problem is that it is overactive, but it is not four-year active. I cannot go and fabricate my Zinc Air Battery, right? Failure number one. I learned some lessons, but I could not achieve my target. I could not go to that target because it's not oxygen evolution catalyst. What I mean, ORR is oxygen reduction reaction. Here is an oxygen evolution reaction. So we move to one, right? That is a trimetallic catalyst. Can we get rid of this one? Again, I have a palladium there. Can I get rid of the palladium to reduce the price of the catalyst? What we have done is we start with the molecule and synthesis a catalyst. Yeah, what we do is that you carbonize it and do a surface engineering by acid treatment. You increase the surface area and you generate a lot of pores and you get a fantastic carbon structures, right? You have a metal, you take out the metal and create a force structure so that you will be able to have your more number of active sites, large surface area, so your catalyst can be more active, right? Now I come here, right? In the previous case, what I said is that is oxygen reduction active. That was inactive towards oxygen evolution reaction. Here I have a catalyst that is active towards both. So this is your oxygen reduction. That implies those who are not familiar, leave it. And your oxygen reduction, here you have your oxygen evolution. The same catalyst catalyze both reaction, oxygen reduction and oxygen evolution. Yeah, we made it. We made the homemade Zinc Air Battery, and we tested. You cycle it, go up to 72 hours, right? Charge, discharge. I mean, cycling, charge it, discharge it, charge it, discharge it. You could get your open circuit voltage of around 1.4 voltage, but it's a little short of the theoretical voltage. Theoretical voltage is, as I have shown, it's a 1.65. Here it is only 1.4. The major problem is that you have a voltage efficiency loss is 18%. That's a huge loss. So I will not be able to achieve anything. I can show as a showcase. Yeah, I have done something. Yeah, it works from the based on the cobalt based catalyst. We moved up to that alloy catalyst. What we have done is again we started with the molecule. What we say here, I have a cobalt chloride and go and you generate your hexacyanobate, your multimetal complex. Again carbonize it. You generate this kind of a catalyst. Okay. Again little advanced. What we have here is a cobalt iron particle encapsulated by a graphite carbon shell. Again, the test is whether it's oxygen reduction active and oxygen evolution active, right? So with the first test is clear. Yeah, this catalyst is active towards oxygen reduction as well as your oxygen evolution. I'm not going to explain you the characterization. Now you go here. Again, what I have here is that the open circuit potential is 1.4 volts, right? I hope I have a time. So in case if I'm crossing the time, either Dr. Vasimalai or Professor.
Yes, sir. This is Vasimalai. So you can take 10 more minutes. No problem, sir.
10 more minutes, right?
Yes,
I will quickly go through that. Okay.
Thank you. Thank
you. Okay. So 1.4 volt. Again, we come here. Your voltage efficiency of 8%. Okay. We move to the other catalyst. Right, we synthesize the catalyst, again surface engineer it, and you have a table describing all the parameter. Again, I will skip that part and then go into the performance. What I have here is you have your oxygen reduction and oxygen evolution reaction, and you get your 1.58 volt open circuit voltage, very close to the theoretical voltage, only 6% voltaic efficiency loss. That's a major achievement. Again, we move to the nickel cobalt. Catalyst, again, we synthesize based on the supramolecular approach, and then you generate this catalyst, and then you go here, and then you do that. We could make up the coin cell based as well as the normal. You could light up the LEDs, and you have only 5% voltaic efficiency loss. Okay, I will skip this one. Now, this is the history that comes there. What we have is a timeline, how it goes there. I'm not going into the detail further. Okay, a little lighter side, right? I mean, if the 10 minutes is there. I will take, I mean, this is one thing that I want to tell you on the lighter side. I'm not sure how many of you heard about the Ramsden, right? The one who discovered the saccharin, right? Nitric acid acts on copper. The story goes by this way, right? Because of the limited time, that what I will do is that I will come back to this one at the end. This is a lighter story. It's a very fascinating redox chemistry story. How he worked with the nitric acid and copper. I will come back to this at the end. Okay. So this is what we have here is that is supercapacitor. So far what I talked about the batteries, I talked about this is a supercapacitor. Right. What we have, again, I will skip this part. What I have already explained about that, the basic fundamental of your supercapacitor. Here what I have, three different one, double layer, pseudocapacitor and hybrid capacitor. Three different types of capacitor based on the fundamentals. Okay. Again, don't bother much about it. If you have any question, you come back to me. I will explain you. So this is the couple of slides I have where I will be able to show that the redox reaction based material that we have synthesized and how we fabricated a supercapacitor device. This is simply based on a galvanic displacement reaction. This is an accidental discovery. The reaction between a potassium permanganate and Br minus, and we end up in getting a beautiful nanostructure that I have shown here. Beautiful nanostructure, right? Nanostructures, and based on that, what we have done, this is the growth mechanism. How it starts with a very tiny particle, goes and come out with a micro particle, big size, made up of a very tiny nanostructures. Okay, this is another one. What we have here is the same MnO4 minus. Again, this is an accidental discovery. That is playing with the redox potential, right? So you will be able to appreciate the redox potential that is listed. You look at the potential, you play with the potential, and then come to a material, use that material for the fabrication of your asymmetric supercapacitor. So this is a device that we have fabricated. And at the end, what we have here is that you are able to have a device. Yeah, this is a demonstration level, and you have your specific capacitance of this and energy density, and your Coulombic efficiency of 90% after 6,000 cycles. That is phenomenal for this material. Okay, right. And this slide, what I'm going to do is that I have talked about the zinc air battery that is made up of an air cathode and a zinc. We synthesize a material which is able to serve in the two different ways. One is as a air cathode and in the supercapacitor. I repeat, the same material I'm going to demonstrate as a air cathode as well as a supercapacitor material. Now I'm going to use, I have fabricated the zinc air battery. We have recharged the supercapacitor that is made up of this material. Okay, so it's basically a tungstate-based material we synthesize, and characterization is here. And you have the supercapacitor fabrication with all that gives you, and you can see here the coin cell based device, how it functions, how we are able to light up, and the mechanism is here. And this, with the same material, what we have done is we have fabricated a zinc air battery. Now you have, what we have is that you have a 1.5 volt as a over potential with the open circuit voltage, and you can charge and discharge for 72 continuous hours. Okay, with the same material. So now what I have shown is here what I have. This is my zinc air battery, as fabricated zinc air battery. I don't need to apply any potential or anything. This I have here. I have my supercapacitor that is as fabricated. I don't need to charge this one because zinc air battery generate electricity. I am going to charge this supercapacitor with the help of the zinc air battery. So you charge the supercapacitor with the as fabricated zinc air battery. And what I have shown here in the images, this side, what we have here is that this is from the supercapacitor charged by the zinc air battery. Okay, now what we have, the recent trend is flexible devices. I will skip this one. Right, we also work on the electrolyte for the fabrication of the electrolyte flexible device. Here we have made the flexible device. Yeah, supercapacitor. This you can see here. This is a configuration of your supercapacitor made up of a gel electrolyte, and here you have your flexible device. A proof of concept demonstration. At the end, what we need is we need a material of different kinds. A long way to go if you want to run your vehicle or run your bike. Like you can look at this one. Again, I'm not going to for the details. Let me give you that. This is about the good enough. So a good teacher always make you do something a little bit more than you thought that you could do. Like you can ponder it and you can meditate on. I mean, think of it, what he meant that. Now, a couple of courses. I go to lab in order to interact with my postdoctoral student to try and can shape them to not copy but ask question. We have to a little dialogue because you don't pretend to be the fountain of all wisdom. As a teacher, we don't need to pretend that we know everything, right? Nobody is perfect. Nobody knows everything. We can frank and go and ask the students and learn from them. I do that. I ask my student and I learn. Well, as I say, I don't believe in everything that you read. Don't be afraid to think at this, all right, to understand what has gone before, but don't just rely on copying, but develop your internal voice and your own internal means of interpreting. My objective was never to make money. I wanted to contribute the human knowledge and betterment. So this, I want to leave this with you as a teachers, those who are listening to me, right? Inculcate this principle, right? Not to copying from somebody, but what we do, that should be the integrity. We should go with the students and then teach the student, develop, and for the betterment of knowledge. In a nutshell, what I have shown in a brief of time, whatever I could convince you that a functional material for rechargeable zinc air battery and the supercapacitor and we synthesize material and the two different devices. And before I leave, I'm the associate editor of this journal. I would request, in your lifetime, you contribute one original article to this journal. And I thank you for your kind attention. If you have any doubt or question, you can ask me. If you have a time, I will go back to the Ira Ramsen, the brief story, a lighter side of the story, if time permits. Right. Thank you very much.
Thanks a lot for your excellent presentation, Professor. And we are very sorry not able to give much time for you. Almost 1 hour 15 minutes is finished. We have to finish our program within 1.5 hours. So 15 minutes time we are thinking to give us a discussion section. So again, I'm very sorry not able to give much more time.
No, it's all right. It's all right. I took a lot
yeah,
of time. It's all right.
Yeah, talk was very excellent. Now I open the session for the discussion. Those who are in Zoom, please unmute your mic and directly talk with our chief guest. Harishankar, please check anybody is raising hand, unmute their mic and give an option to unmute the mic by themselves. And we have received several questions from YouTube chatting box as well as Zoom chatting box, sir. Can I ask that question, sir?
Yeah. You have a time, you ask. What I do,
yes,
I will.
Okay, thank you. This question from Gauri Sankari, madam. How to calculate the storage capacity of battery?
Yeah, storage capacity of battery. Which battery we were talking about? Lithium-ion battery, or is it? I mean, she can write to me. I will give her answer. Within a short span of time, it's very difficult to explain. If it is a lithium or other metal-based battery, what you're supposed to do is that the anode should be completely consumed, and then from the discharge curve, how much is your capacity comes here. Based on that, you can calculate that one. That's one way of calculating. There are different ways. This is one way. Consume all your anode, and from there, that's another way of calculating. I think it will take a lot of time for me to explain. Maybe the questioner can approach me. I will be able to explain. No problem.
Thanks a lot, sir. The participants, anybody want to talk with our chief guest? Please, I am providing the chance to you. Please kindly use it. Any participants?
Hello.
Yes, sir. Yes, you can.
Good afternoon, sir.
Yes.
Sir, what's about your opinion to the replacement of lithium-ion battery to sodium-ion? That's the first question, sir.
Okay.
Second question is how the solid-state battery will improve the performance as well as an capacity as compared to polymer or liquid electrolyte, sir. That's the
Sir,
second
please
question.
introduce by yourself. Where are you from? And
Yeah,
where
I am Venkatesan from. I am working as a project staff in Sikri, sir.
Okay, sir.
Right.
Thank you.
Right. The first question is that replacing lithium-ion battery with sodium.
Sodium,
Yeah, that's
yes, sir.
sodium-ion battery. A lot of people are working on that. But if one concern, the cost of the battery will come down. But the other concern is that sodium is again highly active. You need to have your glow box inert atmosphere to work with the sodium-ion battery. People are working on it is yet to commercially available as lithium-ion battery. The one is that your reactivity, high reactivity, plenty of works are going on. So the works are in progress. Maybe we may be able to get it, but my concern is that safety issue is still a concern because the same dendrite issue is there in the sodium and potassium ion battery. Right. Your second question was, can you repeat that?
Yes, sir. Well, how the solid-state battery will
Solid state
improve the
battery. Yeah, I got it. Right. Solid state battery. Yeah, that's mandatory to get this safe lithium-ion battery or any other battery. The performance is expected to be or known to be less with respect to the conventional batteries, because your charge transfer and then the transport and migration of ion is limited when compared to the liquid electrolyte. But people are working on with a different way. When you mentioned the polymer battery, the polymer battery is very good, but your lifetime is very, very limited. You cannot cycle it, I mean, as you have to do with your lithium-ion battery. That is a limitation is there. People are working on the electrolyte part. So no liquid electrolyte. Now everybody is working on the gel electrolyte or the solid electrolyte. In fact, if you look into the Budanov paper, in the year of 2017, I suppose, he made a glass electrolyte and he made a breakthrough there. I did not bring to here because of the limited time. There are works are going on and people can work on, explore on the electrolyte side. That's one hot area that one can work on that, right?
So, yes, sir. Thank you, sir. And one more question, sir. Is that nitrate is actually in helping to improve the battery for fast charging, sir?
Now, what is that?
Is that nitrate?
Nitride.
Yeah, it's helping to improve fast charging, like 5 minutes charge or 10 minutes charge for battery.
Yeah, that's a debatable question. The fast charging and slow charging is basically electronics, nothing to do with your electrochemistry at all, right? Yeah, people debate on that. This one, that's basically electronic circuiting, right? So basically, if you do fast charging, basically you are killing your battery. That's everybody might have come across, right? Yeah.
Okay, sir. Thank you, sir. That's all.
Other participants, anybody want to talk with our chief guest? Kindly do it.
Yeah, good evening, sir. It was really a wonderful presentation. This is Shahida from Crescent University. So my question is, can I coat graphene and use as an electrode material in lithium battery?
No, I'm not able to hear properly. Your question is, sir, graphene?
Yeah, can I coat graphene material maybe on a copper foil and use as an electrode material in lithium battery?
Yeah, if you can have a stable electrode based on your graphene, that's a wonder, that will work. I did not touch on the graphene based material at all, because I don't claim to be a nanochemistry man, right? I do work on the material, but your question is valid. Many people are working on that one. They quote, we also have done a lot of work, but the stability issue comes into picture. As long as you grow the graphene by CVD method, that will go well. By simply converting your graphite to graphene oxide and converting back to graphene, what we call the reduced graphene oxide, and depositing on the copper foil, may not have a long cycling life. That is my major concern. You may have a different property, absolutely there, but the carbon-based material on that, it will give you. But one thing you need to keep in mind that the graphene itself has a property for charge storage. It will give a capacitance. So that needs to be taken into account. If you are growing on the copper foil by CVD method, the stability will be much, much better. Instead of coating by simple method, that may not have a high stability. That's my observation, that's my experience. I hope I answered your question.
Thank you, sir. Now I can go for the charting box question. Aisha Begum from our Crescent department, Crescent University. Please comment on wireless charging device. Is it hazardous to health?
Hazardous to health, right? I mean, nothing to the health, hazardous or, right? We are dealing with so many wireless things, right? Wireless charging is something like that. So make sure that your frequency, I'm not a expertise in the wireless charging electronics side. Generally, what I will say that, I don't think that is a hazard, wireless charging. But make sure that you go beyond the frequency that your brain or your body can withstand. Wherever, whether your antenna or your charging device, whatever it may be, not restricted to that, your wireless charging, right? I mean, this question should be answered best by electronic or the telecommunication people. So based on my understanding, what I say that, yeah, you look at the frequency should not interfere your body, your brain. That's all, that's all.
Okay, sir. Thank you, sir. And this question was asked by Narendra Kumar. What methodology is suitable to coat graphene composite on classic carbon electrode surface?
Yeah, this is a very fundamental question. Like, graphene composite is basically what you do is that basically what you will be doing, you will be synthesizing reduced graphene oxide, that is graphite converted into graphene oxide, and reduce it back and get your reduced graphene oxide. Right. Coating is spin coating is the best method. Again, the solvent that you use that matters. How you dry it. So don't be in hurry. If you are making with the room temperature, the ionic liquids or the other solvent, you should be patient enough. If you are doing a drop casting, I would suggest you go for a vacuum dry. Or better way is that one is your the spin coating. Spin coating will be give you a uniform coating and pretty stable, again, based on how you handle that. I hope you answered.
Yes, sir. Thank you, sir. Now I am giving again chance to the Zoom link participants. Please talk directly with our chief guest. Anybody? Harishankar, please check anybody is raising hand, unmute their mic. So if not, I can go back to the charting box question, Professor. And this question was asked by Dr. Chandrasekhar. Which type of battery is providing good performance?
Which type of battery providing good performance? Obviously, it's a secondary battery, rechargeable. What we have is now you have a lithium-based batteries, lithium-ion battery, lithium polymer batteries. Now the problem that we have is that, as I mentioned, there are the recharging, all these issues there. So we are inching towards a new generation batteries. There's a metal air battery, or other than lithium, other ion batteries. Even zinc ion battery is coming up. I did not mention here, zinc ion batteries, they are very similar to your lithium ion battery. Obviously, sodium and potassium ion battery people are working on. The safety issue is still a concern. So if you want to have a safety, yeah, now what we have is that lithium ion battery. We don't have a lithium battery, there's a lithium ion battery. We are marching towards the other battery devoid of the lithium.
Thank you, Professor. And this is my question. I have seen many of your data, the reverted cyclic voltammetry curve we have seen from your data. So is it the special case, or what information we can get it from this reverted cyclic voltammetry curve, sir?
Yeah, cyclic voltammetry curve, you mean in the polarization curve, or you are talking about the cycling charge discharge?
Cycling charge discharge.
Yeah, what we do is that you charge it and follow the current. How is the charge? Right? You apply a particular current and follow the charge. How you charge it at a particular time. And then what you do, you discharge it. And then again you charge it. Exactly similar to what your mobile batteries you are doing. Charging, discharging, charge. How long it is stable, how long it can go. That's a test that we do.
Okay. Thank you, Professor. And we have received several questions in the chatting box. Now I can give a chance again to the Zoom link participants. Please unmute your mic and talk with our chief guest. Kindly utilize this opportunity. Somebody is talking, but voice is not audible.
Hello.
Yes, sir. Yes, please.
Hello, Miss. Good
Yes,
afternoon,
sir.
sir.
Yeah. Good afternoon. Good evening.
Hello.
Yeah, good evening.
Yes, sir. You can talk, sir. It is audible.
Sir, how far metal air battery is useful to us, sir?
Metal?
Metal air battery.
Can you repeat the question? Metal air battery?
Hello.
Hello, sir.
Metal.
Yes, sir. Yes, please.
How far metal air battery is useful to us, sir?
Yeah, metal air battery is useful. That I mentioned
To us,
that
sir.
already metal air battery is in use in the hearing aid. Those who are not able to hear, they will have a very small device. This device is function is by the Zinc Air Battery, and the other batteries are other metal air batteries are coming up. For example, in US, in German, these batteries are being commercialized. In a couple of years, you will be able to see that in the market.
Hello.
Your Zinc Air Battery. Yeah, can you hear me?
Yes, sir. We are hearing, please.
Yeah, so your Zinc Air Battery in a couple of years down the line, in maybe 2-3 years, you will be able to see that. If you Google it, there are many companies are making, potentially making and commercializing that. But it is in India, it is yet to come, yet to come.
Okay, sir. Thank you, sir. And I can go for a charting box question. This is Dr. Usha Palanichami. Sir, you mentioned you have prepared Zinc Air Battery and other air batteries. Whether it is taking a large space or it's a smaller space, sir. Occupying large space.
You mean they are talking about question is about the size?
Yeah, size.
Yeah,
size
we have
done
with the both. We first demonstrate with the homemade, the normal cell, the big cell, and then we move to the coin cell type. So the button cell. So we have fabricate the 2 electrode and put in a button cell, punch it, and then test it. We have done both.
Okay, sir. Thank you, sir. One participant is in the line. Please, sir, you can talk with our chief guest. Kindly unmute.
Hello, may I talk?
Yes, please.
Yes.
I want to ask something may not be suitable for the session, but how much potential is required to electrolyze the protein layer of COVID-19 virus?
Yeah, that's $1 million question, right? First of all, I need to know what is the content of this protein, and then what is the potential, what are the functionalities there. Otherwise, I cannot simply say that this potential. That is maybe I am not a specialist on that one. If you know, if I know the protein, what are the proteins and what are the functionalities there, then we can tell that. Right? If it's an aqueous solution, yeah, based on that. But I'm not in a position to give a good, simple answer for that one, because I do not know anything about the protein functionalities. I'm sorry.
Thank you, sir. Thank you. So any other question from participant side? Please kindly unmute and talk with our chief guest. Okay, a few questions are there in charting box, sir. I can go with a little faster. Dr. S. Kalaichavan, sir, asked about what are the biggest challenges in the solid state battery?
Yeah, biggest challenge is that ionic conductivity is a major issue. Ionically conducting electrolytes, the solid state electrolytes, that is a major challenge to achieve. So plenty of gel electrolyte and other electrolytes are available. The conductivity of these electrolytes are limited. As a result, your performance will die. That's one. Second one is the stability of the electrolytes. So how is the potential window that we will apply, how far this electrolyte will be stable. If the electrolyte itself decomposes while charging and discharging, your performance automatically goes down and then it dies. So these are the major challenges, your stability of your electrolytes, and of course the ionic conductivity. Maintaining the ionic conductivity of the electrolyte in a good condition, that is another big challenge.
Thank you, sir. And this question, very interesting question, was asked by Vijay Ushasri. Sir, these days, everybody looking to charge with short times. So what are the materials needed to charge with a very short time?
If in terms of electrochemical energy storage device, if you want to quickly charge and discharge, there is only device available is a supercapacitor. So the supercapacitor is used in the Airbus with the window. If you want to quickly open and quickly close, you need a quick discharge and quick charge. So the supercapacitor is widely used wherever you need a quick discharge to open the window, say for example in the Airbus, and quickly close it. So supercapacitor is the one device that is available now to quickly charge and discharge. Again, this do not be drawn to the mobile battery. Your mobile battery itself contains plenty of supercapacitor, right, along with your battery. Right.
Okay, sir. Thank you, sir. And now we can give a 5 to 7 minutes for you, sir. You said you want to discuss something. Please.
Right. We'll go back. It's on the lighter side, right? I love to tell the story. Right.
Yes, please.
I hope you don't get annoyed by listening to my story. Right.
No,
listen here. Right. What we have here is a nitric acid acts on copper. This is a famous statement. The Remsen was a student, so he read this statement in the book. You know what I'm telling is a story in the year of 1846 to 1927 during his college days. So one day he went to his chemistry lab. He read before that night this one, nitric acid acts on copper. So he was so curious to know what it actually means. So he went to the laboratory. Nobody was there. Early in the morning, before anybody comes, all the windows are closed. The lab, you're not supposed to do any reaction, but he went there. He took his purse, wallet, and picked up one of the penny, the copper coin, and he saw the nitric acid. You know why he has done this? He was just so curious to know that what actually it means. So he put the copper penny on the table, the desk, the working desk, and then he found the nitric acid. He opened the bottle and poured it over the copper coin. I don't know how many of you able to visualize what it would have been, right? As soon as a violent reaction, nitric oxide fumes came, the dark brown color, this one, he never expected. So he was so scared, the entire lab is filled with your dark brown gas. He was scared because if somebody comes there, he will be in trouble. He immediately picked up the partially dissolved coin by his hand and ran to the window, opened the window and threw it away. Okay, now he looked at his finger. Now he understood that. First he understood that how nitric acid acted on copper. Now he saw that his finger is getting yellow color and it's burning. Now he said that I understood that the nitric acid not only acts on copper, but also it acts on finger, right? So he was with the pain, he started rubbing his finger on his trouser, right? I hope you will be able to visualize. If you work in chemistry laboratory, so you can think of that what is the situation of Remsen. So now he rubbed his finger on his trouser. So looked at the trouser, now trouser is gone, right? So nitric acid not only acts on copper, it acts on finger, it acts on trouser. So the lesson learned was that it's a redox reaction, right? So you can experiment it not by this way. If you have a fume hood, right, you go there and take the RB and then try this reaction, right, with a safety setup. You put a copper fillings and slowly add your nitric acid. you will be able to see the beauty of the redox reaction or the electrochemistry, the redox reaction that is happening inside the RB. So what I want to mention here is that on the lighter side, he intended to understand what I mean by nitric acid acts on copper. He understood not only nitric acid acts on copper, but also on finger and also on the trouser, right? This is a redox reaction story. He is the one of the co-discoverer of artificial sweetener, right? What we call this saccharin. So that was basically made by one of his postdoctoral fellow and published, but this was not patented by this Ramsden, patented by the co-discoverer. So Ramsden got nothing, though it is highly popular, right? That's on the lighter side of how nitric acid acts on copper and a brief history of what the saccharin, right? Thank you very much.
Sir, please unmute yourself, sir.
Hello, Professor.
Yes.
So thanks a lot for this story, very interesting story.
Okay.
And thanks a lot for your excellent presentation.
Right.
Still, we have a few questions, but I will, if you give the permission, I will ask them to contact you through email. Then
Yeah.
contact
Ask them to send by email. No issue.
Yes. Dear participants, if I'm not read any questions, please just post that question to our chief guest. Sir will answer for your questions. So thanks a lot for your kind acceptance and come over here during this pandemic period for your excellent presentation. Thanks a lot for your nice talk, sir. Now
Thank
I
you.
hand over the session to, do you want to say something, please?
No, it's a thank you very much, right, having me here in your platform. I hope I did not make the people boring, telling the history and all. Right, I enjoy interacting personally with the students and faculty members, but we are remotely connected. I hope everybody enjoyed the time that I have. Maybe I have taken a little more time than what you have we expected. If you have any question, please feel free to connect with me. As long as I can do it, I will respond. Don't expect the reply immediately. In 1 or 2 days, I will respond surely.
Retna Raj?
Yes.
Oh, thank you for an elaborate, informative lecture. Okay.
Right, thank you.
You are not boring.
Right.
Okay.
So based on the participants' comments in a Zooming box as well as YouTube box, all are written very excellent talk. And one guy, he written a very energetic talk throughout the 1.5 period. You are fully energetic. So
because I'm talking about the energy storage, right? I should want to energize all the people to do work on the chemistry, particularly in the energy, whatever the area.
You energize the people. You energize the audience also.
Thank you very much.
Sir, Dean Madam is inside. Madam Rani Madam.
Yes, sir.
Please unmute the Madam mic. Sir, this Dr. S. Kutirani, our Dean School of Physical Chemical Sciences.
Yes.
Madam want to say hi to you.
Sir, good evening, sir.
Yeah.
Good evening, sir.
Very good evening.
Thank you very much for your lecture, sir. And thank you very much for accepting our invitation.
Oh, thank you. Thank you very much for having me in your platform to interact with your faculty and students. Thanks a lot.
Thank you so much, sir.
Yeah.
Thanks a lot, sir, and thanks a lot, madam. Now I hand over the session to Aisha. Aisha is there? Vengat, please check it.
Yes, I'm checking.
Aisha,
yes, sir, she's there. She's there, yes. Sir. Aisha.
Please unmute your mic, Aisha.
No, she has some problems.
Renita is there?
I'll check Renita, sir. No, sir.
Okay. So I can conclude, sir. So, dear participants and respected speaker of the day, Dr.C.Retna Raj, Professor, Department of Chemistry, Indian Institute of Technology, Kharagpur, and respected Dean, School of Physical Chemical Sciences, Dr. S. Kutirani, respected Head of the Department, Dr. D. Swaramurthy, and dear participants, on behalf of our Department of Chemistry, B.S. Abdur Rahman, Crescent Institute of Science and Technology, I thank you all for your kind attention, and my special thanks to our today Chief Guest, Dr. C. Retna Raj, for his kind acceptance of our invitation and come over and deliver a very excellent talk today during his busy schedule and pandemic period. Tomorrow session will be started at tomorrow 4 p.m. And as I mentioned earlier, if I am missing any question, feel free to send the mail to our chief guest. Definitely our chief guest will reply to you. So tomorrow's speaker, Dr. K.V. Gobi, Professor, Department of Chemistry, National Institute of Technology, Warangal. Thanks a lot for you for your kind attention. Thank you so much today Chief Guest Dr. C. Retna Raj, Professor, Department of Chemistry, IIT Kharagpur. Thank you so much, sir.